When we measure the rate of a reaction, we can measure it usually in one of two ways, either by watching or measuring the concentration of one of the reactants as it's being used up and how quickly it's being used up, or if one of the products is such that we are able to physically observe its formation and measure how much of it we have, we can measure the reaction rate in that manner as well. Being that it's a rate, it indicates that there is a change. In this case, it's a change in concentration per given unit of time. So the units are usually molar, which is moles per decimeter cubed or moles per liter, per unit time, which is typically seconds. Now there are 5 main factors that will affect how quickly a reaction will proceed. The first is the nature of the reactants. Are they ionic or molecular type reactants? The second would be the concentration, or how much of the solute is there in a solution. Third would be pressure. This would apply to gas-based reactions because gases are the only state that compressibility is going to be a factor. Liquids and solids will not be compressible, but the molecules in a gaseous state will be, and thus will have an impact on its concentration. Fourth would be surface area. This will deal with heterogeneous type reactions where you have different phases reacting, like a solid and a liquid, or a gas and a solid, 2 different phases. And finally, the one that most people would probably think of as affecting reaction rate, and that is the temperature of the reaction. When we consider the nature of the reactants, things that are ionic in nature are going to tend to react faster than substances that are molecular in nature. And this is due to the fact that when we deal with ionic substances, those ions are held together by electrostatic attraction, opposite charges. And so pulling those ions apart, if you will, is sort of analogous to taking a magnet off of a refrigerator. You just simply need to apply enough energy or force to overcome that force of attraction, a force of attraction which is usually only effective over a very small distance. And so there's no unentangling, if you will, of the electrons and the electron levels. It simply separate the particles far enough that the force of attraction will let go. Things that are molecular in nature, typically you have a sharing of the electrons, and so when you are breaking those bonds, you need to first unentangle, for lack of a better term, those electrons back to their original owners. Then when they go out and find their new partner for the new compound that they're going to form, if it's going to be another molecular reaction, then you need to have the overlapping of the electron clouds and the sharing of the electrons to form the new bond. Now, regardless of what type of reaction we're talking about, ionic versus molecular, all chemical reactions start off with a collision. The 2 particles, assuming we're just dealing with 2 reactants, the 2 particles need to physically come in contact with one another, collide with one another, and at that point, depending on what the elements are, we'll determine whether we have a transfer of electrons or a sharing of electrons. These collisions, we consider them in most cases to be what we call elastic. And what we mean by an elastic collision is that looking at the whole system, the whole collision system, before the collision and after the collision, the total amount of energy is the same. You may have a transfer of energy from one particle to another, but if you collectively look at how much kinetic energy is present before and after the collision, they are the same. Energy is perfectly conserved. It's not lost to friction, not lost to heat. Now, not all collisions are going to have the same impact. Some are going to be softer collisions, some are going to be harder collisions. And just as when, say you're in your car with the airbags, if you drift into the car in front of you, if you're not going very fast, chances are the airbag's not going to deploy. And that's because the force of that impact was not enough to affect the change of initiating the airbag deployment. If you're going a little bit faster and have more velocity, when you collide, there will be more force in that collision, and therefore the airbags will deploy. Collisions between atoms and molecules are the same exact way. Some are going to have enough energy to affect change, some aren't. When they do have enough energy to affect change, that means that the energy of the collision is equal to or exceeds the activation energy. And when your reactant particles have enough energy that they can reach that summit, when we look at our reaction energy diagram, that kind of intermediate transition state is known as an activated complex. Now, that activated complex is not an actual substance that you can isolate and bottle and keep that separate. It is a very transitional state. It is literally the state where the atoms are in the process of breaking existing bonds and turning around and forming new bonds. Now, if a particular reaction has a high activation energy requirement, that means that very few of the collisions that are going to occur will have enough energy to allow the atoms to form that activated complex. And so, therefore, that reaction will proceed at a very slow rate. The second factor affecting reaction rate is that of concentration. When we talk about concentration, we're referring to the amount of matter that is in a given volume. And usually we're talking about solutions, so our units are moles per decimeter cubed or moles per liter. If we increase the concentration, if we have a higher concentration of solution, that means that we have more solute in a given volume of solution. If we increase the amount of solute, that means there's more particles in that given volume. The more crowded it is, the more collisions there are going to occur, and with more collisions, you have a faster reaction rate. When we talk about concentration, again, we use units of moles per liter, moles per decimeter cubed, and we represent this in an equation by putting the formula for the substance in squared off brackets. So if you had, for instance, NaCl in brackets, that would refer to the concentration of a sodium chloride solution. If we consider a simple reaction, hydrogen plus iodine to form hydrogen iodide, the rate of the reaction, we can calculate the rate of the reaction if we consider the concentrations and also something called a proportionality constant. In this case, it's a specific rate constant represented by K. Now, this is a constant that is experimentally determined. It's determined based on experimental results of when we manipulate the concentration of our reactant, what do we see happening respectively with the rate. And that relationship is a proportional relationship. In order to change that into an equality that we can apply algebraic skills to be able to calculate specific values, we need that proportionality constant, that K, to change our equation from a proportional one to one of equality. So if we consider, seeing that we have a 1-to-1 ratio, mole ratio of hydrogen to iodine, if we were to double one of those two quantities, in this case the iodine, that would mean that it's twice as likely that hydrogen is going to have an effective collision, and therefore the rate we would expect to double. If instead we doubled the hydrogen, again, iodine now is twice as likely to have an effective collision with the hydrogen, so therefore we would expect the overall rate to double. If we doubled both concentrations at the same time, that would mean that there would be a total of 4 different effective collisions that could take place. And if you draw it out on paper and you have 2 hydrogens and 2 iodines, you have them side by side, and you draw arrows connecting all the possible different combinations of collisions, you'll see that there are 4 possible combinations, and hence we would expect the rate to quadruple if we doubled all concentrations across the board. So again, the rate law equation would be, we see as rate is equal to that proportionality constant, specific rate constant, times the product of the concentration of the individual reactants. And so at this point, the take-home message is your reaction rate is going to vary directly as the product of the concentration of the reactant. So if that product is increasing, you expect the reaction rate to increase. The third factor is pressure, and again, pressure only applies to gas-based reactions. If we increase the pressure on a sample of gas, effectively we're squeezing that gas and we're forcing it into a smaller volume. Now, presumably that sample of gas is a fixed sample with a fixed number of particles, so forcing those particles into a smaller volume means that they're becoming more crowded. If they're becoming more crowded, you're going to increase the number of collisions, and with an increase in the number of collisions, you increase the reaction rate. The fourth factor is surface area, and again this relates to heterogeneous reactions. We know that reactions require collision, so the only possible place for a large piece of a material to have that collision is at the surface. And this can also be made analogous to a physical process of dissolving. Think, what is going to dissolve faster, a sugar cube or granulated sugar, assuming we have the same mass of sugar? And the answer is the granulated sugar, because the individual sugar pieces are much smaller. So much more of it is able to come in contact with the water, and it's able to be dissolved into the water much faster. With the sugar cube, only the sugar that's on the face of the cube is going to be able to be dissolved. And the same holds true for a chemical reaction. So by increasing the surface area, effectively we're increasing the concentration, the number of molecules that are available to undergo an effective collision. And thereby we are increasing the reaction rate. The fifth factor, and probably the most common one thought of affecting reaction rate, is temperature. Temperature is the average kinetic energy of all the particles in a given sample. So if we have an increase in temperature, that means we're increasing the overall kinetic energy of the particles. If there's more kinetic energy in those particles, then more of the collisions are going to have that sufficient energy, that activation energy, to be able to affect change. And with an increase in the number of effective collisions, that means that the reaction rate will increase as well. Another way that we can speed up a chemical reaction is through the use of a catalyst, and this is called catalysis. How a catalyst works is it's not physically involved, it's not chemically involved in the reaction. It itself is not used up. However, what it provides is an alternate mechanism. It changes the route that the reactants can take to get to the products, and it does so in such a way that the activation energy requirement is lower than it would be without it. So what you see here in the diagram is a representation of an endothermic reaction with a very high activation energy. But if we were to add a catalyst, how this diagram would change is that activation energy hill would be much lower. And so you start with the same reactants, you end with the same products, the same bonds being broken and reformed. However, that energy requirement to get to the activated complex is now much lower. So a higher proportion of the collisions are going to be effective collisions and thus lead to a faster reaction rate. Sometimes we want to slow down a reaction, not speed it up, and so we may use an inhibitor. What inhibitors do is they don't stop the reaction, they simply tie up the reactants or the catalysts and prevent them from reacting or from allowing reaction to be sped up. And by preventing these from occurring, this helps to slow the reaction down. So a good example would be preservatives that are used in foodstuff items to lengthen the shelf life of different objects. We can also think about cooling systems, refrigerators, freezers. The whole reason we have those and it increases the longevity of our food is because that decreased temperature slows the chemical reactions that are involved with spoilage.